Welcome to AutoProject Insights. I'm excited to have you here today. This presentation is all about exploring the latest developments and insights in automotive project management. We'll cover key strategies, innovative tools, and best practices to help you drive success in your projects. I'm looking forward to sharing valuable information with you, so let's get started. Today's topic is design verification, or DV for short. This is a critical phase in the development process, where we ensure that our design meets all specified requirements. It's about making sure everything functions correctly before moving on to production. Design verification helps us catch issues early, saving time and resources down the line. Throughout this presentation, we'll explore the key techniques and best practices involved in DV. By understanding this process, we can improve the quality and reliability of our final product. So let's dive into the core concepts of design verification and see how it fits into the bigger picture of our development cycle. What is design verification, or DV for short? Well, it's a crucial step to make sure that a product's design fully meets all the specified requirements and functional specifications we've set out. Think of it as a quality check to confirm that everything is on the right track. It's not just about the design looking good. It's about verifying that each output, whether it's a circuit, a piece of code, or a mechanical part, matches the original design input. This step is essential before we move into production or validation, because it helps catch any discrepancies early on. Ultimately, design verification gives us confidence that the final product will perform as intended and meet all our standards. This process ties back to our overall goal of delivering reliable, high-quality products to our customers. So, let's talk about when design verification actually happens in the automotive component development process. First, we have the concept phase, which is all about initial ideation and assessing feasibility. This is where we start shaping our ideas and making sure they're viable before moving forward. Next is the design and development phase, and this is where design verification takes place. During this stage, we verify that our designs meet all specified requirements before moving into final testing. Then comes the validation phase, which is focused on final product testing to ensure everything functions as intended in real-world conditions. Finally, we reach the production phase, where manufacturing begins and the actual components are produced at scale. It's important to remember that automotive component development is a multi-phase process, and design verification is a crucial step that happens specifically during the design and development phase. This ensures that the product is on the right track early on, reducing risks down the line and aligning with our overall goal of delivering safe, reliable automotive components. Let's talk about the DV testing approach we use to ensure our systems are robust and reliable. First, we have physical testing, which involves testing real-world components on dynamometers and test benches. This means we actually use the hardware and sensors in a controlled environment to see how they perform under realistic conditions. It's a crucial step because it gives us tangible, hands-on data. Next, we have software simulation. This is more of a virtual testing process where we use CAD models, thermal analysis, and stress simulations. These tools help us predict how the components will behave without needing to build physical prototypes every time. It allows us to identify potential issues early and optimize designs before moving to physical tests. Both approaches are essential and complement each other perfectly. Physical testing provides real-world validation, while simulations allow us to explore a wider range of scenarios more quickly and cost-effectively. Together, they form a comprehensive testing strategy that helps us improve performance and reliability, aligning perfectly with our overall goal of delivering high-quality, dependable systems. Let's take a closer look at the inputs that go into our DV test plan. First up, we have OEM requirements. These are the specifications provided by the original equipment manufacturers, and they set the foundation for what our design needs to achieve. It's crucial to understand these requirements thoroughly to ensure our testing aligns with their expectations. Next, we consider the design concept. This reflects our understanding of the intended functionality of the product. Knowing how the system is supposed to work helps us identify potential failure points and areas that need rigorous testing. Then, we look at DFMEA findings, which stands for Design Failure Modes and Effects Analysis. This is a systematic approach to pinpoint possible failure modes in our design and assess their potential impact. By analyzing these, we can prioritize testing efforts where they're most needed. Finally, we have safety requirements, encompassing regulatory and safety standards. These are vital because they ensure our product not only performs well, but also adheres to safety regulations, protecting users and meeting legal obligations. Together, these inputs form a comprehensive foundation for our test plan, guiding us to develop effective testing strategies that validate the design and ensure safety and compliance. Now, let's take a closer look at the engine DV test parameters. First, we have the test description, which covers the main aspects we're evaluating. The purpose of these tests is to ensure the engine performs reliably and efficiently under various conditions. Acceptance criteria set the standards we need to meet for each parameter to consider the engine compliant. Moving on to the power output test. Here we're measuring the maximum power and torque across the entire RPM range. It's crucial that these values stay within plus or minus 3% of the target specifications, as this indicates the engine is delivering consistent performance. Next is the fuel consumption test. We evaluate how the engine performs at different loads and speeds to verify that it meets the targeted fuel economy. This helps us confirm the engine's efficiency in real-world scenarios. The idle stability test assesses how smoothly the engine runs when idling. Our goal is to maintain a stable idle speed within plus or minus 50 RPM, ensuring smooth operation when the vehicle is not in motion. Finally, the cold start test examines how well the engine starts at degrees Celsius. We aim for the engine to start within 3 seconds without stalling, which is critical for reliability in colder environments. Altogether, these parameters form a comprehensive framework to validate engine performance, efficiency, and reliability, key themes that run throughout our testing process. Now, let's walk through the physical test for power output. First, we mount the engine securely on the dynamometer, making sure it's properly connected with fuel, cooling, intake, exhaust systems, and the ECU. This setup ensures we can accurately measure the engine's performance under controlled conditions. Next, we connect all the necessary sensors. These include torque, RPM, fuel flow, exhaust temperature, and ECU data logging sensors. These instruments are crucial for capturing detailed performance data throughout the test. Once everything is in place, we perform a full load sweep. This involves gradually increasing the throttle to 100% watt or wide-open throttle while measuring at specific fixed RPM points. This process allows us to see how the engine performs across its entire power band. Finally, we generate power and torque curves from the data and compare them to our target values. Our goal is to verify that the engine's output stays within plus or minus 3% of the desired performance targets. This step is essential for confirming that our tuning and modifications are delivering the expected results, tying everything back to our overall goal of optimizing engine performance. Let's take a closer look at power calculation. When we perform this test, we're comparing the target power to what we actually measured. For example, if the target is 80 kW and we measure 78 kW, that's considered a pass because it's within 3% of the target. It shows our system is operating as expected. However, if the measurement drops to 74 kW, that exceeds the 3% margin, and it's a fail. This helps us quickly determine whether the system is meeting our performance standards. Now, moving on to repeatability. It's important to run the test multiple times, ideally 3 times, to ensure consistency. We then look at the variance between these runs. The key point here is that the variance must be less than 1.5%. If the variance exceeds that, it indicates the system's performance isn't stable enough, and we need to investigate further. Overall, these steps are crucial for validating both the accuracy and consistency of our system's power output, ensuring reliability before we move on to other phases. Let's talk about the software test for thermal simulation. First, we create a 3D model, which forms the foundation of our analysis. Then, we build a detailed thermal model by incorporating material properties, ensuring accuracy in how heat interacts with different components. Next, we apply conditions by defining heat sources, such as combustion at over 2,000 degrees Celsius, and cooling inputs to simulate real-world scenarios. With everything set, we run the analysis, which can be either steady state, to see the final temperature distribution, or transient, to observe how temperatures change over time. Finally, we validate the results by checking for hot spots or any thermal limits being exceeded, confirming that our design maintains safe and efficient thermal performance. This process is crucial for optimizing thermal management in the overall system. Now, let's take a closer look at the thermal simulation outputs. First, we have the temperature maps, which show the distribution of heat across various components. You'll notice the metal temperature distribution, highlighting where the engine parts are hottest, as well as the oil and coolant temperatures, giving us insight into how effectively the cooling system is working. We also see the exhaust temperature profiles, which are crucial for understanding heat flow and potential stress points. Moving on, one of the key benefits of these simulations is hot spot identification. For example, the exhaust port region can exceed 250 degrees Celsius, and gasket regions sometimes surpass safe limits. Recognizing these hot spots early allows us to address potential failures before they happen. Next, we examine the thermal stress plots. These are vital because they help us predict where cracks, gasket leaks, or deformations might occur due to thermal expansion and stress buildup. By analyzing these plots, we can assess the risk levels for different areas of the engine. Finally, the simulation results serve as a guide for making targeted design improvements. We can incorporate cooling ribs to improve heat dissipation, upgrade materials to better withstand high temperatures, redesign the water jacket for more effective cooling, or enhance the oil gallery to improve oil flow and heat transfer. Overall, these outputs are essential tools that help us optimize engine performance and durability by addressing thermal challenges proactively. Now, let's look at the key outputs and deliverables from our design validation process. First up is the DV test report. This document is crucial because it provides a comprehensive record of all the test results, measurements, and analysis findings. It essentially captures the performance and reliability of the design under various conditions. Next, we have the design change requests. These are documented modifications that may be needed if any failures or issues are identified during testing. They help us track what needs to be adjusted to ensure the final product meets all requirements. Then there's the final approval. This is the formal sign-off that confirms our design has passed all tests and meets the specified requirements. Once approved, it's a green light to move forward with production. Finally, we have the updated CAD files. These include revised 3D models that incorporate all the approved design changes, ensuring everyone is working from the latest version and that the design is ready for manufacturing. Together, these outputs ensure a thorough and organized transition from testing to production, aligning with our overall goal of delivering a reliable, well-documented final product.